Let's explore the fundamental trigonometric ratios using a right triangle. In trigonometry, we use the sides of a right triangle to define ratios that describe the relationships between angles and sides. In this right triangle, we have three key sides: the opposite side shown in red, which is across from our angle theta, the adjacent side shown in green, which is next to our angle, and the hypotenuse shown in blue, which is always the longest side opposite the right angle. The relationship between these sides gives us our basic trigonometric ratios. The sine of theta, or sin theta, is defined as the ratio of the opposite side to the hypotenuse. This gives us a value that depends only on the angle, not on the size of the triangle. For our current angle of 30 degrees, this ratio is exactly 1/2. The cosine of theta, or cosine theta, is the ratio of the adjacent side to the hypotenuse. For a 30-degree angle, this value is approximately 0.866, or more precisely, square root of 3 divided by 2. The tangent of theta, or tangent theta, is the ratio of the opposite side to the adjacent side. Interestingly, this can also be calculated as sin theta divided by cosine theta. For our 30-degree angle, the tangent value is approximately 0.577, or 1/3 of square root of 3. These numeric values help us quantify the trigonometric ratios precisely. Let's now connect our right triangle representation to another fundamental concept in trigonometry, the unit circle. The unit circle gives us another way to visualize and calculate these same values. In the unit circle, the x-coordinate of any point on the circle equals the cosine of the angle, and the y-coordinate equals the sine. This is because a unit circle has radius 1, so the hypotenuse of our reference triangle always equals 1, making the trigonometric ratios directly readable from the coordinates. Now let's observe how these values change as we adjust the angle. Notice how the values change as the angle increases. The sine increases from near 0 to approaching 1, reflecting the growing height of our triangle. The cosine decreases from near 1 toward 0, showing how the adjacent side's proportion of the hypotenuse shrinks. Most dramatically, the tangent increases rapidly as we approach 90 degrees, because the opposite side grows while the adjacent side remains constant. This behavior occurs because when we approach a 90-degree angle, the triangle becomes increasingly tall and narrow. These trigonometric ratios are powerful tools that help us solve problems involving triangles, circles, and periodic phenomena. They form the foundation for more complex trigonometric identities and applications in physics, engineering, and many other fields. Let's explore how the Pythagorean theorem leads to one of the most important trigonometric identities. We'll begin with a right triangle that has three sides. Side A, shown in red, is opposite to angle theta, side B in blue is adjacent to theta, and the green side C is the hypotenuse, which is the longest side of our triangle. The Pythagorean theorem tells us that in any right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. So we can write a squared plus b squared equals c squared. To connect this to trigonometry, let's divide each term by c squared. This gives us a squared over c squared plus b squared over c squared equals c squared over c squared. We can rewrite this as the quantity a over c squared plus the quantity b over c squared equals 1. The fraction c squared over c squared simplifies to 1. Now here's where trigonometry comes in. In a right triangle, we define sine of theta as the ratio of the opposite side to the hypotenuse, which is a over c, and we define cosine of theta as the ratio of the adjacent side to the hypotenuse, which is b over c. When we substitute these trigonometric relationships into our equation, we get sin² plus cosine² equals 1. This fundamental relationship is known as the Pythagorean identity, and it works for any angle theta. Let's visualize this identity using the unit circle to gain a deeper understanding of why sin² plus cosine² always equals 1. In the unit circle, we have a circle with radius 1 centered at the origin. For any angle theta measured from the positive x-axis, we can place a point P on the circle. What's special about this point is that its coordinates are exactly cosine theta and sine theta. If we drop a perpendicular line from point P to the x-axis, we create a right triangle. The x-coordinate of point P, shown in blue, is cosine theta. The y-coordinate, shown in red, is sine theta. These coordinates come directly from the definitions we saw earlier. To visualize the Pythagorean identity, we can construct squares with sides of length cosine theta and sine theta. The blue square has area cosine squared theta, while the red square has area sine squared theta. According to our identity, the sum of these areas should always equal 1. What makes this identity so powerful is that it holds true for any angle. Let's watch how these values change as we rotate through different angles, while the sum of their squares remains constant at 1. As we rotate through different angles, observe how the sizes of the squares change. When sine gets larger, cosine gets smaller, and vice versa. But remarkably, their squared values always sum to exactly 1. This is the geometric meaning of the Pythagorean identity, and it works for any point on the unit circle. Let's explore how we can derive the tangent identity directly from the Pythagorean identity through some algebraic manipulation and geometric reasoning. We begin with the Pythagorean identity, which states that sine squared theta plus cosine squared theta equals 1. This fundamental relationship connects the primary trigonometric functions and is rooted in the Pythagorean theorem itself. To transform this into a relationship involving tangent, we'll perform a clever algebraic step. By dividing every term by cosine squared theta, we can introduce the tangent function, which is defined as sine theta over cosine theta. Let's simplify each term in our equation. The first term, sine squared theta over cosine squared theta, equals tangent squared theta, because tangent theta is sine theta over cosine theta. The middle term simplifies to 1 since any number divided by itself equals 1. And the right side, 1 over cosine squared theta, equals secant squared theta, since secant theta is defined as 1 over cosine theta. To better understand the geometric meaning of this identity, let's visualize it using a right triangle. This will help us see why this relationship must be true from a geometric perspective. In this special right triangle, we've chosen specific values for the sides. The adjacent side has length 1, which serves as our reference. If we set the adjacent side to 1, then according to the definition of tangent, the opposite side must have length tangent theta. Similarly, by the definition of secant, the hypotenuse must have length secant theta. Now let's connect our algebraic identity to this geometric representation. The first term in our equation, tangent squared theta, corresponds to the square of the opposite side's length. In our triangle, that's the square of tangent theta. The constant term 1 in our equation represents the square of the adjacent side's length, which we've set to 1, so its square is also 1. And finally, the term secant squared theta corresponds to the square of the hypotenuse length. This makes perfect sense when we apply the Pythagorean theorem to this triangle. The Pythagorean theorem tells us that in any right triangle, the sum of the squares of the two legs equals the square of the hypotenuse. In this case, that's precisely tangent squared theta plus 1 equals secant squared theta. This shows that our algebraic derivation aligns perfectly with geometric reality. We've now derived one of the key trigonometric identities. Tangent squared theta plus 1 equals secant squared theta. This relationship holds for any angle theta where these functions are defined, and it gives us a powerful tool for simplifying trigonometric expressions. This identity is particularly useful when working with problems involving tangent and secant functions. It allows us to convert between these functions and helps simplify complex trigonometric expressions in calculus, physics, and engineering applications. Let's start with the fundamental Pythagorean identity, which states that sine squared theta plus cosine squared theta equals 1. This relationship is the foundation for many other trigonometric identities. This identity directly connects to the Pythagorean theorem in a right triangle. If we consider a right triangle where the hypotenuse has length 1, the opposite side has length sine theta, and the adjacent side has length cosine theta, then by the Pythagorean theorem, sine squared plus cosine squared equals 1. To derive the cotangent identity, we'll perform an algebraic operation on the Pythagorean identity. Specifically, we'll divide every term by sin²θ. This is a common technique when deriving trigonometric identities, dividing by one of the squared functions. When we divide each term by sin²θ, the left side becomes sin² over sin² plus cosine² over sin², and the right side becomes 1 over sin². Simplifying the first term, sin² divided by itself equals 1. For the second term, we can rewrite cosine² over sin² as the square of cosine theta over sine theta. The right side remains as 1 over sin²θ. Now we need to recognize two important trigonometric ratios. The ratio of cosine theta to sine theta is defined as cotangent theta, and the reciprocal of sine theta is defined as cosecant theta. These definitions will help us express our equation more elegantly. By substituting these definitions into our equation, we can rewrite the second term as cotangent squared theta and the right side as cosecant squared theta. This gives us the cotangent identity, 1 plus cotangent squared theta equals cosecant squared theta. Now let's visualize this identity geometrically. We'll create a different right triangle to directly illustrate the cotangent identity. In this new right triangle, we're setting the opposite side to have length 1. This special case makes it easier to see the cotangent and cosecant relationships directly. When the opposite side has length 1, the adjacent side must have length cotangent theta, and the hypotenuse must have length cosecant theta. This is because cotangent theta equals adjacent over opposite, and when opposite equals 1, the adjacent becomes exactly cotangent theta. Similarly, cosecant theta is hypotenuse over opposite, so when opposite is 1, the hypotenuse equals cosecant theta. Applying the Pythagorean theorem to this triangle, we get that the square of the opposite side plus the square of the adjacent side equals the square of the hypotenuse. Since the opposite side is 1, that gives us 1 squared plus cotangent squared theta equals cosecant squared theta. And that's our cotangent identity. 1 plus cotangent squared theta equals cosecant squared theta. This elegant relationship emerges naturally from the Pythagorean theorem when we consider a right triangle with an opposite side of length 1. This identity is extremely useful in simplifying trigonometric expressions and solving problems. It's one of a family of related identities that come from the Pythagorean identity through similar algebraic manipulations. We've seen how the cotangent identity connects algebraic manipulation to geometric intuition. By dividing the Pythagorean identity by sin²θ, we derived an important relationship that can be directly visualized in a right triangle where the opposite side has length 1.